Okay. Hello, everyone. Thanks for coming. Hope you had a good lunch. You're not too sleepy. My name's David Brimley. I'm a senior solutions architect for Hazelcast. And today, the subject of the talk is high performance in-memory Java with open source. So, just a bit of background on me, so I won't bore you for too long. As I said, I'm a senior solutions architect for Java. 17 years I've been doing Java development now. So I've been working on that for a long while. Unfortunately, I started out as a COBOL programmer, and that's something I don't want to ever go back to, but I did that in 1988, and it was a way into IT for me. And then a few years back, I learned to code. I started out as a kid learning BASIC on VIC-20s and BBC Model Bs. So, they were quite good computers, actually, the VIC-20, not a bad machine. And then Oracle Coherence. I've worked on Oracle Coherence, so if you've ever used an IMDG, you may have come across Oracle Coherence. And Pivotal Gemfire. So this is my third now in-memory data grid. So actually, before we go any further, can I just do a quick show of hands? How many people who have actually used an in-memory data grid, so something like Oracle Coherence or Gemfire? Okay, so maybe about a third of the room. Okay, so today's talk, I'm going to be talking about high performance in-memory Java, and that's really, as it says, I think it's an IMDG. Some people may disagree. And then we'll talk about getting to grips with Hazelcast, and we'll talk about a tour of the features of Hazelcast, and I'll just give you some IMDG tips. So some stories of my 7 or 8 years of developing in the area, and the things I see people do and fall over with. So, in-memory Java, two things really that make an IMDG, and it's really the two C's, caching and compute. And then the thing that makes it all magical is the D you stick in front of that, and that's distributed. So distributed cache and distributed compute, that's IMDG. And this thing evolved really over a period of maybe 10 or 11 years. And when we began, we all started writing Java programs, and we was maybe writing a client-server system against a database, and we didn't want that read to keep going to the database every time. We've all done it. We wrote a simple Java program with a hash map maybe, and just stored some values in the hash map. And of course, the results of that are out of memory problems. And then along came, some open source software projects, and it was still a cache in one process at that point, but it had things like eviction, so it would save you the out memory problems. Then along came distributed cache, and that was a way of scaling out horizontally, so you could have many Java processes that contributed into a cluster. You could grow your cluster, and subsequently the size of the data you could store in a cache became a lot larger. And then distributed cache. Well, what I was going to say there is distributed compute. Now, we had this situation where we had a large distributed cache, so many JVMs, and you could then go and get the data from those JVMs. And of course, that became quite costly. You was doing network operations, you was going into the cluster, grabbing data, performing some kind of mutation or computation on it, and then pushing the results back into the cluster. So lots and lots of network hops, lots of operations to deal with data sets. And that's when distributed compute came along on top of that. Everyone realized it would be a better idea really to put all of the compute back onto where the data resides. Rather than bringing the data to you, you go and push your function, your compute where the data is. So that was distributed compute. And then where we are today is really, I'm calling it big data IMDG now. We have a situation where we've got distributed compute, we've got distributed cache, and with the advances that we've got in terms of off-heap storage for the JVM, and ways that you can bypass OSs for faster inter-process communications, you can bypass sockets, you can do very big data sets, and you can do them very fast operations. And big data as well, of course, is possible because of, we all know memory is getting a lot cheaper. nowadays you can quite easily have terabyte machines of memory and add those to clusters. So the qualities of an IMDG, what are they? So ideally, as we said, it should be easy to scale. And IMDGs, you should be able to scale them not only horizontally, but you should be able to scale them vertically now as well, so with things like off-heap. So previously you had a JVM, you could have maybe 5, 10 gigabytes on the JVM before you started getting problems with garbage collection. Now with off-heap, you can make those JVMs a lot larger. It should be fault tolerant. So when you store your data in that in-memory data grid, it's stored in a distributed structure, so a distributed map. To give yourself the scalability, that map entry goes to one JVM in the cluster. Now, you need some kind of fault tolerance. It's no good if that JVM dies and you lose your data. So an IMDG should store a replica or a number of replicas on other JVMs. And if that JVM dies, you should still maintain your data. Performance as well is very important. It's in memory, so it's very, very fast. It's a lot faster than going to a database that generally would read from a spinning disk. And lastly, in my opinion, should have an easy-to-understand API. There are a number of, you can compare and contrast things, but the API should be natural to a developer. If you're working in Java, you want to be working with Java APIs you know and understand, right? So this is where I want to talk to you about Hazelcast. Hazelcast is an open source Apache 2 license project. And we provide Java collections and queues, but they're distributed. You can run a hash map or a set or a list, and that will be distributed in the Hazelcast cluster. So you can horizontally scale it, you can vertically scale that structure. We have Java concurrency as well, so if you're used to working with things like semaphores, countdown latches, just general locking in conditions, again, we have that. That's distributed. So you can have a distributed lock in the cluster. And then what you want to do as well is you want that cluster to be able to talk to other systems as well, other data stores. So an IMDG ideally should be agnostic about the data stores that it deals with and the systems that it can interact with. So you should be able to persist and read from anything. So when you're working with a cache, you work with maybe a distributed map, let's say in Hazelcast, you do a map put. That entry then should go into the cache and then potentially go into any other kind of backing store that you could create. So this is why I say there in the red that you can persist and read from anything. So you can persist to a relational database or a file or any of those other things. And then, obviously, you've got all this data in all of these data structures, and you want to be able to query those things out. So, you're working with maps. You can get this stuff out with a key, but you might not know the full key. So you want to be able to do SQL-like queries. Okay. So we provide a SQL-like query language, and you can build predicates as well. So if you have a Java object, you can look at the properties of that object. You can index the properties of that object, and you can query on them as well. And then just a few other things. We have topics as well. So if you don't want to go through the pain of setting up a huge pub/sub infrastructure, and you just want some simple pub/sub, you can use that out of the box as well. And then lastly, we have a rich set of event callbacks. So pretty much anything that goes on inside the cluster, you can get a callback on it. So you can get a callback on any kind of mutation on your data structures. You can get a callback on things that are actually going inside the cluster. So if a node joins or leaves the cluster, you can get informed about that. So the event callbacking system is very important, and especially if you want to maintain relational data structures, then the callbacks are the way to do that. So, as I said in one of the earlier slides, you want something that's really, really easy to use. Okay. So Hazelcast, there's two things you need to start up a Hazelcast cluster. If you use Maven, that's the only dependency you need. It's just one dependency. Hazelcast doesn't depend on any other projects. It's just everything is coded by Hazelcast committers. Okay, there's no other third-party dependencies. You can download the zip and just get the jar if you want it, of course. And that's the line of code you need. That will start up a Hazelcast JVM, just the one line. By default, Hazelcast has a default configuration XML file that configures all of the data structures for you. If you want to define your own, obviously you can. You can just pass in your configuration file there. Or you can configure via Spring Beans, and you can do programmatic API configuration as well. So that's that. I just wanted to talk, or actually before we do that, I just wanted to give you a quick demo of that, about how, to show you how easy that is to get going. So if I flick off this, and I'm going to go over to the terminal. You can see that, can't you? So what I've done is I've just gone to the hazelcast.org website. Okay, so you can just go down. You can go to hazelcast.org, and then there's the download. So you can download the zip, or you can, as I said, you can do the Maven dependency, and that's exactly what I've done on this machine. And I've unzipped, and if I go over to here, I've unzipped, and there's a Hazelcast. There's a bin directory, and I'll just run up a Hazelcast node. Now, Hazelcast is starting now, and the way it tries to discover other nodes in the cluster is by default, it will use multicast. Okay, so the Hazelcast JVM will start up, it will ping out on multicast over the network, and it will say, is there any other Hazelcast clusters there? Any Hazelcast JVMs? If there are, they have the same credentials, because you want to, obviously in multicast, you might not want every JVM to join the cluster, you want to separate them, but if the credentials match, then they will form a cluster. And you can see this is the first one I've created, so it's the only member on the network at the moment. So I'll go over here and do another one. We'll just say run. Now this run script that you get by default, it's kind of a demo application. So it's doing pretty much what I showed you there. It's doing a Hazelcast instance in the main method. And it gives you this command line at the bottom here, so you can have a play around with some of the data structures. So that's what I'm going to do now. So if I just do a help, this is not really, blue's not good colour, is it? Is that better? Let's try that. So is that clearer? I can never tell. So on here, you can see all of the data structures and some of the other distributed compute features, and you can it's a really good way of getting to know Hazelcast and getting to learn in-memory data grids in general. So you can see there's queues, sets, locks, maps, lists, and we've got some atomic longs and a few other things, and executors as well, which is part of distributed compute. So if I say in here now, I'm going to do a map put, I'm going to do 1 London. So I'm placing something into a key and doing map put 1 London. Now this is coming up here now because I've got this cluster also in my XML file configured to replicate to another cluster. I haven't got that one running yet, so that's why we're getting that. So if I go over to the other node, there's London. Okay. Now it can see that we work on partitions. So a distributed hash map, we work with partitions. By default, there are 271 partitions in a Hazelcast cluster. And Hazelcast, when you put something into a map, it will decide what partition it goes on. And Hazelcast knows, I've got 2 machines there, 2 JVMs. Those 271 partitions will be divided across those 2 JVMs, okay? And it will take the key, it will hash the key, it will mod it by the number of partitions, and that will give it a number from 1 to 271. And because we know which partitions are on what machine or what process, it can put that entry onto that partition, onto that machine. So I can be in any JVM, and I can get that record out. The other thing it gives you is the fault tolerance. Obviously, we spoke about backups. What it will do by default, Hazelcast out of the box, all of your data structures, it has one backup, one replica defined by default. So if I was to close one of the JVMs down now, the data would reappear in the other JVM. So to visualize that, I want to show you something else. There's something that comes in the distribution called the management center, and that's a WAR file. And if you just drop that WAR file into any servlet container, I've just dropped it into Apache Tomcat, you'll get this. And I'll log in here. Let's just connect. There we go. And there's the two JVMs that we started. And you can see over on the left-hand side here, here's all of the data structures. And because I haven't configured any explicit namespaces for my data structure, so I haven't created a configuration for a map called trades, for example, it just uses the default. So there's a default setting for all of these structures. So my data, if I go to that map's default, my data should be in there. And there it is, okay? And you can see that it's distributed, okay? So there's my main entry, and there's the backup on the other machine, okay? And there's all sorts of other nice things you can see on here. So you've got things like the backups, the memory, the throughput, and you can do some simple querying via this map browser as well. So let's go in here. There's another one here we can do. We can say map put many. I'll put 1,000 records in there at 1024. Okay. So if we go back over here now, this is pushing information. So the JVMs push their stats to the management center via a REST API. Okay. So you're not polling the cluster nodes continually. So that can cause you problems. So we push, when the nodes in the cluster are ready and they've got some time, they'll push their stats out to the management center. And here you can see now that we've got that data distributed. Okay. So if I kill this JVM now, that's just a hard kill. That will disappear and it will push again in a second. And this will come back to 1001. There you go. And that's because we had the backups on the other machine. So you can build out clusters like this. You can be in a running system with users adding and removing data and running functions and reports and distributed compute. And you might decide that, you've got some new data sets coming online soon. So you can just dynamically add new JVMs to the cluster and everything will balance itself out. So that's a very, very basic look at, what we have. We also have queues, there's topics, multi-maps as well. Multi-maps is a good one. If you've ever used Guava multi-maps, we have a distributed version of that. So if you've ever gone through the pain of having a key with a set as a value, and you need to mutate or manipulate values in that set, there's 3 or 4 lines of code you have to write to do that, right? You've got to get the set, you've got to get the value out of the set, you've got to mutate it, put it back into the set, and then put the set back in the map. So we provide an atomic one call to do that. I'll answer a question. We'll do 5 minutes for questions at the end. So that's multi-maps, and as I said, we have executors as well. So let's just go back to the presentation. If I can find it, there we go. So that very, very basic data structure there, right? I mean, where are we? Why isn't that moving on? That's it. Right. So that's basic, data structures. And then we have distributed compute, okay? So there are 3 ways of doing distributed computation operations inside Hazelcast. You've got executors. So if you've ever dealt with Java executors, the interface will be completely familiar with you. You can take a runnable or a callable, and you can send that out into the cluster. Okay. You can do entry processes, and that's a way of doing per key based distributed compute operations. And we'll look at all of these in a moment. And then finally, as of about a month ago, we've got MapReduce, and that's a Hadoop-like API where you can run MapReduce operations inside the cluster. So there are 3 ways of doing distributed compute. So, as I said, the executor, the interface is iExecutor service. It can have a runnable or a callable. And most importantly, with this is you can do targeted execution inside your grid. So you can say to your executor, I want to run this runnable or callable, and I want to run it on only particular nodes in the cluster that have some keys that I'm interested in. Okay, so you might want to do some mutation on some data sets. That runnable or callable will be sent out into the grid, and because Hazelcast knows where those keys are, it will only run on those JVMs where the data is. Okay? If you just want to do raw distributed compute and you want to pass your data alongside your runnable or your callable, so you're not dependent on any data inside the grid, then you can just decide you want to run it on a number of members. Okay? So you're not key dependent. You can say, I want to run this execute on this block of members inside my cluster. So you could have a dedicated compute farm inside your cluster if you wanted to. So this is the code you need to do that. This is a very basic example, but it gives a general idea. We're going back to our line where we create our member. So that's firing up a Hazelcast instance with all the default settings. And then with the Hazelcast instance we can just get an executor service, and you can give it a name. Okay? So we're just calling it my executor service, and that will use the defaults for the executor service. So with an executor, you'll know that you can configure a number of threads, and then there's a queue as well you can configure. So that's just using all of the defaults for that. And then finally, we're just going to say executor execute, and that's just going to run some kind of echo task that will do a system out inside the cluster. So that will run on every single JVM, and it will do a printout of some kind of system out. But you can pass in there any kind of runnable or callable. As long as everything's serializable and it can move over the network, you can pass anything along with that you want. And then entry processor. Entry processor is really an atomic way of executing a runnable or callable. Well, it's not a runnable or callable, but it's a way of executing code in an atomic way on a key-by-key basis. So what Hazelcast will do is you implement an entry processor interface, and you say, I want to run it on a particular set of keys. Hazelcast will go off and distribute that around the cluster, and it will call per key that entry processor's method on the machine. And that gives you explicit locking as well. So because we know what key we're providing you, we can lock that key as we go through it. And this runs via the IMAP interface as well. So a very, very simple example there, but on the IMAP interface, you say, I want to execute this entry processor on this key. And it will go off into the cluster, find the JVM that it's running on that key, and it will run your entry processor. And then MapReduce. It's kind of new. It's been out since 3.2, which is about a month, 2 months old now. Hadoop-like API. We're going to have aggregators as well. We're going to have a whole bunch of aggregators coming along with 3.3. So you can do standard things like min, max, counts, that kind of stuff. And there'll be a custom aggregation API on top of the MapReduce as well. And then we're going to have scheduled tasks as well, so you can run scheduled MapReduce jobs as well. So again, some more code. This one here is a bit more complicated, but the actual, the one that we're interested in here is where we actually run our job and we submit it at the end. You provide a mapper, a combiner, and a reducer, submit it, Hazelcast will do the rest for you. And it will distribute that job all out into the cluster, find the correct nodes to run it on, and it will run those processes for you. So that was distributed compute. As we said as well, you want to be able to have your in-memory data grid persist and read from anywhere as well. And that's a fairly easy task to achieve. You would implement something that we call a map store interface. You just configure your map to use that map store interface. And then Hazelcast, whenever you do a read into the map or an update to the map, it will interact with that map store interface that you've written. So there's a bit of coding for you to do. You can, with that interface, you can connect to pretty much anything. So here's an example. We've got a map. We're connecting a map store up to it. So here's my class that I've written, my map store. And we'll talk about these parameters in a moment. But you can see there's indexing. So you can index on any property of a map. We'll talk about this write delay in a moment, actually. So then here's an example of the map store. You can see it's got the key and the value of the map as a generic, and there's a store and a load method, and then you just write your code to your data access layer if you've got one, or if not, you can write the SQL or whatever you want right in there. And just on the bottom there, you see we've got, couldn't fit it all on, but we've got delete, load all. There's more methods you can interact with your backing store. So that can be connected to a database, a file system, anything you want really. So whenever a map get is called, and we don't find it in the cache, it's a cache miss, the key's not there in the cache, Hazelcast will call this method load, and it will pass the key that you used in your map get down to this method. And then you can do your lookup in your backing store, and it will return the record back up the call stack, put it in the cache, and return it to the map get. Similarly with the store, you save a record or you do a map put, it will call store. So the other thing, actually, let me just rewind. One thing I didn't talk to you about was this thing here, write delay seconds. Now, what you can do with the map store is you can have this being called synchronously or asynchronously. Okay, so when I do my map put, if I have it synchronously, the map put won't return to the user until we've gone all the way through the stack, we've put the record in the map, we've called our store method, and you've saved it to a database maybe, and then you call back up the stack. That's synchronous from top to bottom to the database. Now, if you've got a particularly slow database, you might not want to do that. So you can set this to be asynchronous. So when you do the map put and it goes into the cache, that's it, you're done. The user gets the return. And at some point in the future, Hazelcast says, okay, I need to save this record off to the database now, I'm going to call the map store. And that's what this write delay seconds is. So I'm saying on this one, just wait 30 seconds and then do the database save. Okay? So then you can have very, very fast updates, but you're still going to persist to the database. So, how long have we got? 24 minutes. Standards. There's a standard you might have heard of. It's called JSR 107, JCache. And that I think it's got the dubious honour of being the longest ever running JSR. I'm not quite sure how long it runs for. I think it was about 8 or 9 years. And it went up and it became dormant and it started off again. And our CTO, Greg Luck, he's one of the co-spec leads along with a gentleman called Brian Oliver, who works for Oracle. And JSR 107, the easiest way of describing it is it's JDBC for caching. Okay? So where you've got a common interface that you can write to databases with, JSR 107 JCache will be the same thing. So the idea is that there's a common interface and you can do map puts, gets, and you can plug and play with your underlying cache implementation. So you can plug a Hazelcast in there, or you can plug someone else in there, and you don't have to do any code changes. It was ratified about 4 or 5 weeks ago, I think, or somewhere in that order. We're working on our version of that now. So this summer, Hazelcast will be JCache compliant. So if you are thinking about starting on a greenfield project and you think you want caching, but you're not quite sure what vendor you want to choose for that, or which project, open source project, it's a good idea maybe to use JCache so you don't have that lock-in. You can easily plug and play. And we're on GitHub. In fact, all of our code is on GitHub. As an open source project, you can see all of the Hazelcast code. We're on GitHub, and I'll show you that in a second. In fact, let's do that now. So if we, oops, here we go. So here's Hazelcast. So it's github.com/Hazelcast. That's the main project, just there, Hazelcast. That's where all of the open source stuff is. And then if you go into Hazelcast, and then we have a branch here called JCache Preview, okay? So JCache Preview is where we're building all of our JCache stuff. So if you grab that branch from GitHub and you build that, and then you plug that into the JSR 107 implementation, which is over here. So this is the official GitHub repository for JSR 107. You build the JSR 107 spec, you should be able to run that demo class against Hazelcast. Okay. So that, in fact, why don't we? This is a bit dangerous, but let's let's try and do it now. In fact, so I've downloaded the demo JSR 107, and what I've done. Let's bring this up. I'll put that in presentation mode so we can see that a bit clearer. Oop, there we go. So there's the JavaX cache API. So that's the JCache API, and we're using this 101 snapshot that they've got at the moment. And I'm using my branch, that JCache preview of Hazelcast 33RC1, and I've done a Maven install, so that's running on my desktop. And if we come out of that, here we go. There's these demos that you have here, right? And there's one of them called cache demos. So JCache, actually, let me just explain a very quick bit about JCache. JCache provides you with the ability to agnostically work with maps. Okay, so you can do map puts, gets. It's type safe as well, so it enforces type safety on those maps. And it also implements entry processes as well, and it also implements things like the map store, so the database interaction that we looked at as well. So they're the main features. And it also has a programmatic API. So let's just look at this code. It's worth just looking, because this is quite important to understand. So JCache starts off with these couple of commands up here. There's a get caching provider. And then when you have your caching provider, you call get cache manager. And that's the thing that returns you the implementation specific version of the cache manager. Now, if you don't pass anything into this signature here, it will do a class loader, and it will try and find the implementation for you. You can also pass into here the implementation specific configuration file. So as I said, Hazelcast can be configured via XML files. So you could pass in the Hazelcast XML file there, and underneath the scenes, Hazelcast would fire up and it would read that configuration file. Now, if you don't want to do that, you can programmatically configure your caches as well via the generic JCache API. So here's an example of it here. We're setting up this mutable configuration, and there's some settings here. So there's a set store by value. So inside your cache, you can the spec mandates that you can have store by value or store by reference. Here's the type safety part where we're doing the strings and the integers, and you can set expiry policies as well here. So there's a whole set of JCache expiry policies. And then finally, we're just doing something really simple. We're getting the cache. So we're saying, get me this simple cache, and we're enforcing the type there again at the end. And you can see there, it's just a simple map after that. It's just doing a cache put or cache remove. But again, as I said, the beauty of it is you can take in a vendor or an open source project, plug in another one. So it's great if you want to do evaluations or benchmarks or stuff like that. You can do that via the JCache API. So if we were to run that now, it's not going to do a lot, but you should just be able to run that, and then let's just debug that. Here we go. So there's the caching provider, and then what should happen is, actually this might be a bit problematic because I've got another cluster running, so this might go a bit haywire actually. But and it's on another version as well. There's the cache manager, okay. So there's the Hazelcast instance. So that would be, you could use some other open source project, and that would bring you back the other one. Now we go through the config. It's got the cache, and you just do the put, and that's it. That's all there is to it, really. That's JCache. But it's very important for you guys if you want to start working with caches, because you'll find that as you look at the APIs of the various caching projects, some of them can differ quite a lot. Not so much with the map maybe, but if you start doing entry processors or any some other distributed compute, then the APIs you wind up having different implementations of that. So that's quite an interesting thing you need to be aware of. So we're on the home run now, and I'll be able to go and have a beer after this. This takes a little while to fire up, this PowerPoint, when you flick to it, which is a bit annoying. Still not doing anything. Here we go. Here we go. Right. So very, very quickly, just some IMDG advice. Really the most common thing, so one of the most common use cases that you use an IMDG for is when you've got a slow database or a hard-to-scale database, and you want to stick a cache above it, okay? One of the most common mistakes, it's not so much a mistake, but just something to bear in mind is don't try and take your RDMS schema, your relational schema, and turn it into the same thing inside the in-memory data grid. Don't create, think about how you're reading the data. So don't create a map per table and then try and do huge joins in the grid if you can get away with it. The other thing as well, and again, this is a thing that we've all been taught over the last 10 years. It's been drilled into us that we have to keep everything relational and everything. A table should just represent one thing. You come from that background and you're mutating several tables in one go. You must have a transaction. They always tell you. You can do transactions. It's part of Hazelcast. It's part of. It was going to be part of JCache. But just think to yourself: do I really need to pay that transaction cost for every single put I'm doing into my structure? Okay. Can I recover from that? If I do get a failure, can I recover quickly from that? Can I write some code to recover quickly from that failure? Is it a problem if someone reads, a bit of stale data from one of the maps for a few seconds? So transaction costs can be quite high. So just think about that. And then we've spoken about distributed compute. Execute near the data. Okay. Don't write clients to your cache and do lots and lots of map gets and bring all the data back on 5 or 6 different maps, work on that, and then send it all back over the wire again. That's what distributed compute was for. But there's still a lot of people that do that. They'll write a client and they'll do exactly that. Okay? That really slows you down, so don't do it. Just send the code to where the data is. And then, because we are going on the wire, think about serialization. Now, all of these caches and the JCache API mandate that everything has to be serializable. So you can just stick a Java serializable interface on all of your data objects, and it will work just fine. But it'll be quite slow. So you find whatever in-memory data grid you use, you find that most of these people will have their own versions of serialization, their own interfaces and implementations. So just look at those and consider using those. Do some timings on them, and you'll find that your time across the network and your operation times, your transactions per second will rocket up. Maybe look for an open source project as well that allows you to do plugs in your own custom serialization. So some do, some don't. Hazelcast allows you to do that. So you could plug in something like a cryo serialization, for example. Now, cryo gives you a very good performance, and it provides you with compaction as well, very good compaction. So just when you are working up your systems and starting them and doing some testing on benchmarks, Just look at serialization. You'll be amazed at the performance increases you can get by picking the right serialization. And then finally, think about your JVM and think about what it's doing, okay? Garbage collection is going to kill you, right? We all know that. But think about the cluster and the JVMs inside the cluster. What's happening to them? What data structures have you got stored on them? Have you got data that's ticking really, really fast? There's maybe a small set of data, but it's ticking rapidly. You've got some FX spot prices, for example. There's maybe, 200 of those things, and they're quite small. But they're ticking really fast. They're generating a lot of garbage. So tune your JVM appropriately. Give yourself a nice big chunk of Eden to do that. What you don't want is a lot of garbage, temporary objects going over into old generation, okay? So just think about a few of those things. So that's pretty much it. At IMDG, so something like Hazelcast, we've only really scratched the surface. It's an incredibly powerful tool, and you can leverage it to solve quite a few use cases. As I said, the most common use case it solves is the unscalable RDBMS, okay? But you can do compute-intensive tasks with it. Web session replication is a common use case as well. So you can have a user's web session and you can have it across a grid, so you don't have to keep going to the same web server. You can use it to create high availability services as well. So you could, using distributed locking, you could have two JVMs come up and one of them grabs the lock and provides the service to your user. If that JVM dies for whatever reason, the lock will be grabbed by the other JVM, and that will keep your service up and running. That's quite a common use case, actually. And then lastly, WAN replication. You can have clusters all around the world. So you can give your local users local speed. You don't have to send that user that's in your New York office over to the London cluster anymore, or a London system. You can set WAN replication between all these clusters and get your New York user to read the New York cluster. He saves something in that cluster, it will just go straight across to London. And these things should be easy to set up as well. So look for a solution that allows you to set up something like WAN replication in 3 or 4 lines of configuration. So that's pretty much it. Last slide, I think. Just some websites for you. And there's the vendor alert slide. That's the vendor alert, that one there. Hazelcast.com. So com's the business for Hazelcast. So we provide production support, papers and webinars off of that site. Hazelcast.org for open source. And then there's our GitHub repositories. And this one actually is worthwhile. If you are interested in learning about Hazelcast, that's the one I always send people to. Hazelcast code samples. Because the API is very intuitive, if you're a Java developer, there is a book for it, but I don't think you even need the book. You can just download that, look at the code sample, you pretty much get it right away. So that's a good resource for you. And then finally, if you're really a masochist, you can follow me on Twitter, where I just generally talk about Hazelcast and what's coming up. So that's it. I can barely breathe. We've got 8 minutes left. We can do some Q&A for 8 minutes if there's any questions. Okay, so the question was where is Hazelcast deployed and what are the typical sizes? So it's a real range actually. In terms of sectors, business sectors, it's because it's kind of a tool. There are some sweet spots for it. So financials, gaming, healthcare, but we see it across a range of sectors. It doesn't seem to be one or the other. In terms of sizes, you can run. We've got JVMs running with just two JVMs with some simple caching. And then in the financial sector, we've got clusters of thousands of JVMs running a compute grid. And that goes up to terabyte scale. So, there's a lot of people using it. There's big intensive applications, and then there's smaller departments that just use it for a bit of caching over the top of a database or high availability services. It's quite popular to do that as well.
What is the default topology? Is it master-slave, or we have different master and some slave?
Yeah, okay. So you're talking about the backups, are you?
Yes, and that will lead to another question in terms of the DR policy.
Yeah.
What is the DR policy? Let's say we have two master and different node. Let's say one cluster goes down.
Yeah.
And we have some distribution between the backup.
Mm-hmm.
We have some update.
Mm-hmm.
Now the cluster came back in.
Mm-hmm.
How does Hazelcast replicate all the updates?
Are you talking about split brain?
Yes.
Right, okay. So to answer your first question, when you bring up the JVMs, all of the there's no concept of master-slave in terms of the replicas. All of the JVMs contribute some of their space to backups and some of their space to primary. Okay, so that's how it works, and it just works like that out of the box. You don't have to say, this JVM is going to be handling all of my masters, and this group of JVM is going to be handling backups. Okay.
How does the data be distributed between the cluster?
Across the cluster. So all of the JVMs start, they can join either via multicast, so that when they want to join, they say, they can do that over multicast, or you can have a set of TCP/IP addresses that you can say this is where the cluster lives. So they all join like that. And then once it's joined, they'll talk to each other via TCP/IP, okay? And then an entry goes into that cluster. It does the modding and the hashing, and then it decides which JVM it goes to, and then Hazelcast will put a backup somewhere else. And that backup can be configured to be, depending on your risk appetite, you can make that backup transfer be synchronous or asynchronous to the main put as well. And you can also configure where the backup goes. So what you want to do is you want to give yourself as much fault tolerance as possible. So if you've got two machines, you can tell Hazelcast to put the backup on the other machine. It will always go on the other machine. Or you can say, always put it on the other rack. Or if you really want to, you can run it, as long as the data centers are quite close together, you can potentially run it across data centers and put the backup on the data center so you survive a complete data center outage. But going back to the split brain problem, and this will be something where if you try and run a cluster across a network, and especially a data center where you might be going through, 2 or 3 switches and a whole bunch of hardware, and you get a wobble in that hardware, you potentially get a split brain situation where the two clusters think they're independent of each other, and so you get the same key being updated in the two different clusters, and then at some point, the switch and the network will resolve itself somehow, and the two clusters will go, there should be one cluster really. But then you've got the problem where you've got key A over there and key A over there, and potentially being different values. So at that point, you need to merge the two. Okay, you need to merge that value across the two. Hazelcast provides you with a map merge callback, and you can write code. Hazelcast will give you the records. It will give you the map entries. Okay, so it will say, here's a map entry from here. Here's a map entry from there. What do you want to do with it? And you can return some kind of object out of it. So you can look at the properties in the two, and you can decide how you want to create your new object. So there's some defaults for that as well. You can use, there's a default map store where you can say, just always pick the last one that was updated, or always pick the last one that was read. Or you can do your own kind of merging as well. So that's how we handle split brain. It's not perfect, but those types of situations don't occur that often, thankfully. And in general, I would, try and run your clusters and the machines in your cluster. Try and keep them as close together in your network, just for speed, really. So we've got 3 minutes left. If there's any more questions.
Sort of continuing a little bit from split brain. One of the features of flavouring Hazelcast a bit. One of the features I used was the distributed locking.
Yeah. Yeah.
You get a split brain situation, you need to have two clusters using that resource.
Yeah.
Is there any way to detect
Is there any way to detect
it?
an external resource being locked? So the situation is one of the clusters has grabbed the lock and it's continually got it and it never releases it.
Well, it's only one's allowed to read from the database at a time.
Yeah.
And it's split Of course, those two clusters, the lock is then different, so two machines could get it at the same time.
Right, I see, yeah. That's interesting. I can't, off the top of my head, think of a way to resolve that at the moment. Yeah. But, yeah, let's chat afterwards about that, and we'll see if we can plug you into some engineers who can resolve that for you. All right. 2 minutes? No? No? Oh, we've got... I'll give you the money later.
Do you have this Hazelcast program is what is special serialization, which you can use directly default serialization, or the default serialization is the Java serialization?
Well, you can use anything you want with Hazelcast. So you can plug in a serialization technology like Cryo. You can do that, or protobufs if you want.
Yeah, and the default one is it the Java serialization?
Java, well, yeah, you can use Java serialization, so you can implement Java serializable on your objects that your objects that you're storing in the map if you want to, or you can implement Hazelcast has its own serialization that you can implement as well, and you just do the from data and the to data methods to serialize in and out of the properties. Yeah. Okay, time's up, 0. Finished. Thank you very much.